I decided that I wanted to show you, instead of continuing with the machine learning stuff, I decided I wanted to show you a real static analysis where we do cool things. So we're going to do liveness property. I know, but I told you to keep it close. I don't know what to say. How close? I don't know. I told you. It's going to be awkward. Anyway, is this okay? I don't know. Sorry. So, liveness properties, okay, as we saw yesterday, I don't even remember now, it basically specified that something good will eventually happen during the program execution. We'll mainly talk about termination, but there are other kinds of liveness properties that we can care about. If we have time, we will talk about them. Two kinds that were proposed by Manna and Grady many years ago are the guarantee properties and the recurrence properties. So they propose a whole hierarchy of properties, actually, but I will not get into more hierarchy, at least of properties, of semantic theories, not properties. And so the guarantee properties basically specify that something will eventually happen at least once in the program. Program termination is one example, but there can be others. In recurrence properties, they require the good thing to happen infinitely often in the program. So starvation freedom is one example. But yeah, let's talk about termination. Why do we care about proving program termination? Well, if a program doesn't terminate, we could have systems that become unresponsive. So this happened some time ago. There were these media players by Microsoft that somehow stopped working exactly on 31st of December 2008. And the reason was basically some piece of code that was computing the date in the device. There was not accounting for the fact that this was a leap year. And so the device just went into a loop and it was completely used. If we have non-termination, we can also create denial of service attacks. And we can have this happen in the Apache server. And we can have also service interruptions, like the Azure Storage Service, for instance, in 2014. Nothing against Microsoft, it's just examples that come with it. Okay, so for termination, let's say we want to make things a bit more formal. There are two kinds of termination that we could care about. On the one hand, we have potential termination. So you can say a program, we need the program to have the possibility of terminating, so to have at least one execution that is finite, so that we take the maximal trace semantics of the program, we check the intersection with the all finite sequences of states, and this should be not empty. And the definite termination, we want all executions of the program to be finite. The distinction is only valid if we have non-determinism in the program. If there is no non-determinism, they are essentially the same. So we're going to focus on definite termination, mainly because we don't have the time to do anything else, I think, in this part, and I don't know if we're going to finish definite termination. So how we prove termination? Well, this is Turing and Floyd told us this a long time ago. We essentially need a ranking function. So we need a function that maps states in a program to the state. This is a well-founded set. You can think about natural numbers or ordinals. Natural numbers is the simplest for now. So you have a mapping from states to this natural number, and the value of this function decreases during the computation of the program. And since they are well-founded, there is a lower bound essentially in the set, a least number. Eventually, the value of this function will decrease, will arrive at this element that cannot decrease anymore, and the program will terminate. To make it a bit more concrete, I'll give you an example. I don't think this is important. Is it important? I don't know. I'm sorry, I don't know how to use this microphone.
It's kind of working.
Microphone, yeah, okay, whatever. Example. So we have a variable x that we just assign a random value to, and while x is, I don't know, greater than 1, yeah, we decrease the value of x by 1 every repeat. So the states are these ones here. We have 4 labels, and for each label we have an environment. This is the transition relation. I'm sorry, I'm again using arrows between, this should be pairs, but it's just, I find it clearer to put an arrow, but this is just think of it as a pair. I will fix it later. Okay, now we can define the ranking function for this program. So the function is going to map states to ordinals, and for simplicity, we partition it with respect to the program points. This way we can define a function for each program point. So at the end of the program has terminated, so we are at 0 steps to termination, so any environment is mapped to 0. At program point 2, this is the loop head. Now the termination depends, or actually the steps to termination depend on the value of x. So if the guard of the loop is false, we will terminate in 1 step. We have to evaluate the guard and then exit. And otherwise we will terminate in a number of steps that depends on the value of x, which depends on how long we will take spend in the loop. And why is there a 2 factor there? Is essentially because I'm counting steps every assignment and every expression evaluation. So for each loop iteration we have 2 steps, the assignment and the expression evaluation. Okay, program point 3 is essentially the same thing, except that we are 1 extra step to termination because we need to do the assignment, then evaluate the expression and then exit. And now the important bit is at point 1. Here we have essentially, we're assuming, yes, sorry, I didn't say it, we're assuming we are working with mathematical integers for the variable. And so we have essentially here all possible numbers of steps to termination. So at program point 1, we need 1 more of all possible numbers. And so we need to go to ordinals. We need 1 more than all possible integer numbers. We will make it more precise later on, but for now, this is roughly how we define a ranking function. I'm sorry. Okay, let's do the termination analysis. Again, it's going to be 3 steps, and it's going to be very complicated steps at each time. So it will take a long time before we finish all of the steps. Just be prepared. So first of all, the concrete semantics. It's a liveness property, so we're going to have to work starting from the maximal trace semantics. And I'm sorry, but we're going to have to see another hierarchy of semantics. I wanted to show you all of it, actually, but I decided to spare you this part. This part is the potential termination part, so we're just going to do this part here. It will be enough. It should be difficult, so it's okay. So, maximal trace semantics, you have seen it already. This is what you have seen before. The set of all executions of the program, finite and infinite, right? We can define it as a fixed point like this, and we start from all infinite sequences of states, and then we add all the suffixes, finite suffixes, ending in a block state, and we restrict the finite sequences, the infinite sequences, sorry, to be infinite traces of the function. So in our example, this is going to be our maximal trace semantics. So we have finite traces, where we stay a finite number of, yes, sorry, I changed the example actually. Now I made it, yeah, because I wanted to do something different. So now we have a random choice of the loop. So we pick a number. If this number is different from 0, we enter the loop. And otherwise we exit. So whenever we draw a number and it's 0, we exit. So we don't always terminate. And we don't know how long we stay in the loop. It depends on whatever. There's non-deterministic choice that we make at every loop. So we have, in the maximal trace semantics, these are the sequences, the traces that we have. So we can stay a finite number of times in the loop and then exit, or we can stay an infinite number of times in the loop. So we have finite traces and infinite traces. All good? Yeah.
Two questions. Does that star scope over both of the tuples behind it, so that it's 1 to 1 to 1 to 1?
Oh, no, just to 2. So from 1, you go to 2. Oh, actually, no, yes. Maybe it's supposed to stay, yeah, it's supposed to be both of them.
The second question was, if you go back one slide,
Yeah.
I think I was still a little bit confused at why we want to consider programs that start at E if the program always starts from A for liveness properties.
Oh, you mean
I think
this thing?
Yeah, like why?
Oh, it's just the way the semantics is constructed. This is suffix close, so we just build everything from the suffixes.
Okay.
It's just because we build it starting from the blocking state, and then we keep adding to it. And we always add them back. So we always build all the suffixes of all the executions over loop. That's all. It's just we have suffixes around. We don't necessarily need them, but yeah, how it works. Okay, so now we need to, as I said yesterday, the maximal address semantics essentially is our shopping cart with all the clothes. But we don't care about the color of the clothes or the materials or whatnot. We care about the price. Here we don't care about what the program is actually doing. We care that it terminates. So essentially, what this path is doing is specializing the semantics. So it's throwing away information that we don't need, so that we can build a semantics that talks about the termination of the program. So that first of all, we're gonna only keep the traces that terminate. Only keep the traces that terminate, and then we will build a ranking function on these traces. This is going to be this part here. But yeah, let's look at the traces. And this part here is actually, so all this alpha here, in this particular case here, we don't actually have a Galois connection. We only have the alpha in this case. This is one real case in which we don't have an concretization function, we only have an abstraction function. And the abstraction function is very complicated, as you can see, because the point is, there we need to keep all the traces that are finite in our semantics, but we also need to exclude all the traces that have a prefix in common with a trace that can be infinite. There will be an example later on, will make a bit more sense. But the idea is, okay, we consider these are all the prefixes of a trace. And this neighborhood here is basically considering a trace and another set. And it's basically collecting all the traces in the set T that have a prefix in common with the trace T. And now what we're looking at is the traces that are infinite in the T. And we want them to not have any prefix in common with the finite trace that we're keeping. So it's not enough to just keep the traces that are finite. We just need to make sure that there are no non-deterministic choices that lead us to non-terminating traces, because we are proving definite termination, not just potential termination. I'll show you an example. Let's say we have this sets of executions here. So we have a finite trace AB, another finite trace ABA, another finite trace BB, and an infinite trace BA. Now, if we do the abstraction, this will only keep the first two, because the second one, this BB, has one prefix in common, this B here, with an infinite trace. From B, we can actually branch to an infinite execution, so this B trace is not okay to keep.
What does the epsilon mean? In the third,
this one, it's the empty trace. And I'm removing the empty traces, because otherwise I will have a match with the empty. Because the empty trace is always a match with, it's always a prefix of another trace. So I just want to non-empty prefix. Yeah. Okay, so just to bother you 1 second, you don't need to remember this, but just for completeness, we only have alpha. It's actually not Scott continuous. It has other problems. So we cannot use actually the clean fixed point transfer theorem. We need to use another one, which is this mess here. It just has different assumptions. We need to actually have, instead of complete partial orders, we need complete lattices. We need f and f sharp to be monophonic functions. And alpha has to be a complete metamorphism, so it has to preserve the loop instead of the join. Has to satisfy this condition, which is not exactly the correspondence. We just need to know that whenever we apply alpha and the abstract function, we are smaller than doing f first and then the alpha. And then there's this post-fixed point correspondence. So essentially, each abstract post-fixed point of the abstract function is the abstraction of some concrete point, post-fixed point of the concrete function. It's a very other assumptions essentially that we needed, but if we satisfy these assumptions, we can actually do the fixed point transfer again.
Sorry, can you repeat one more time why we can't use the Caterina theorem?
So in the Caterina theorem, what we need, the Caterina fixed point transfer theorem, we need the alpha to be Scott continuous,
Okay.
so to preserve least double bounds, and this particular alpha here is not. It's not Scott continuous. I don't have the proof right now on hand, but you can try to find a couple examples. And so if we cannot use that theorem, we need to use this other messy one. And if we have that as an exercise behind this other thing, we can do the fixed point transfer, so we can have that if we do the fraction of the maximal trace semantics, we do get this termination trace semantics. Okay. If we apply the abstraction here, this is the maximal trace semantics, we get an empty set. In fact, this program doesn't satisfy definite termination, so it is correct, because this 1, 2 here is a prefix in common with this other sequence here, which is infinite. Good. And now we do the ranking function built on top of the traces. So now we throw away essentially all the traces that are potentially non-terminating. So we only keep the ones that are definitely terminating. And now we need to build the proof that the program is terminating, which means building a ranking function. And that's the idea for the definite termination semantics. I'm not sure if there is a gamma here, so I only put the alpha. The idea for the alpha is essentially we are counting, we have all these traces, we're just counting all the steps back from the end of the traces to the beginning. These are all finite traces, so we can just count how many steps it takes. And the definition of it is also a bit messy. What I can show you actually is the fixed point definition, which is more intuitive. So you can ignore the alpha for the moment. I just wanted to point out this part. So here the order that we're going to use for the fixed point iterations is this one, and it's going to be different from the approximation order that we will use afterwards when we do the abstraction. So here we're building the fixed point essentially by starting from a function that is defined nowhere. So the domain of the first function, the iterations will be empty. And then we draw the domain, and we also draw the value of the function. I'll show you the fixed point, it makes a bit more sense. Let's work over it with an example. So let's say we have these executions here. These are two finite executions. This is an infinite execution. Okay, this is sort of the fiction of the execution. And so all of these branching here are non-deterministic choices. So we said we start the fixed point from a totally undefined function. I'm sorry, I didn't write it down here, but we start with a totally undefined function. And now the function starts to be defined with value 0 at the blocking states, the states that have no success, where the product is already terminated. This is where we are. And now we have to basically count backwards, one by one, the previous steps. So we have to take the domain of our function, the states that are already in the domain. We take all the predecessors, but now we take the predecessors that, I can put the definition, sorry, the predecessors that already have a successor in the function. So essentially, whenever there is a non-deterministic choice, we want to make sure that all the choices that we take are already in the domain of the function. For all of those, we take the value of the function plus 1, and we take the maximum of the function. So for instance here, we're going to add this state here, because this one has only one successor. So we're going to do 0 plus 1, this is the value of the state. And this one we don't add it, because this successor here is not yet in the domain of the function, so we cannot add it here. At the next iteration, we can add the state. This is the value 2. We are at most at 2 steps in the worst case determination. So if we go down here, it takes 2 steps. If we go down here, it takes 1 step, and we're done. And then this is a fixed one. None of the states can be added to the domain of the function, because this one, this state here has one choice that leads to an infinite execution, so it cannot be in the domain of the function. So all of the states that are now defined, that belong to the domain of the function, are the states from which we know the definite termination holds. And the other ones outside, we know that there is at least one execution that doesn't count. And this is what the theorem says. So if we have a set of initial states that we care about, the program satisfies that determination only if this set of initial states is in the domain of the function that we define. Okay. So this definition, and now I just want to make it a bit more concrete, make it work on an actual program. We worked on transition systems here. So I'm going to give you the denotational formulation again. But this is useful because we'll give you an intuition for how the abstraction will work afterwards. So to make it simpler again, we're going to not define it by states to ordinals, but we're going to partition it. So we're going to do it for each program point in the program. We're going to have our input function. And so we're going to have this transformer for each statement in a program. So for assignments, for instance. For assignments, what we need to do is to make sure that when we do the assignment, it's already in the domain of the function. And in fact, we have to make sure that whatever value the expression that we are assigning takes, we are in the domain of the function. We have to do this pre-field checking that all successors are already in the domain of the function. If we do that, then we can take, as we did in, as we saw in the fixed point, we take the value of the function in the successor state, plus 1, and we take the maximum. Everything else is undefined. So I'll show you an example here. I should have drawn it. Okay, I'll try to make it very quickly here. So I have this function. So the function that I have defined is as value 2 when x is equal to 1. So this x is 1 and okay, this is where my function is defined with value 2, and when x is equal to 3 is value 3. Okay, now the assignment that we are considering is this one. So we are saying x is equal to x plus a random choice between 1 and 2. Okay? So this is a bit confusing sometimes because we are going backwards, right? So we have to figure out where we can define the function before the assignment. So what are the environments where we can define the function to make sure that afterwards, when we do the assignment, we are still in the domain of the function. So it's defined, the function after is defined where x is equal to 1 or 2. So let's say before the assignment, we have x equal to 0. Okay, if we have x equal to 0, we do the assignment. Okay, I'll do it like this. If you do the assignment afterwards, we can have x equal to 1 or x equal to 2. So this is okay. They are both in the domain of the function. And so we can define the function on x equal to 0. And the value of this function is going to be 3. We have to do 2 plus 1, 3 plus 1, and take the maximum. So it's going to be 4. This is the value that we're going to keep. This is the result that you see there. Why is it not defined for other values? Well, let's say you have x equal 1. If you do the assignment, you get x equal 2 or x equal 3. Now the function is defined for 2, but it's not defined for 3. So you have one successor that is not in the domain of the function, so you have one option picking 2 there, for which the program doesn't care. Yeah.
So what we're trying to do is figure out which possible values of x we could have come from.
Yeah, exactly. And we have to pick. I cannot close this one. Okay. Yeah, we have to figure about which values could we come from, and we maintain termination. This is the okay, if you get this idea, then the rest is similar. It's just a bit more complicated because we have different paths to the problem. So essentially, this is an if then else. Now we have various cases, depending on whether when we evaluate the expression, we end up in a case that is always true, always false, or maybe both. Just because there could be a non-deterministic choice in there, and so we could have multiple values. So let's say in an easy case here, for instance, whatever for all values for which the expression evaluates to, the values do not satisfy the condition. So we are always in the case that we don't satisfy the expression. Here we just take whatever function we have there and we increase the value by 1. If we are in the case where we satisfy the condition always, we just take the function, we go to the body, whatever function we get there, we evaluate it and we take the value plus 1. The complicated case is the first one, where we have some values that can go on one side, some values that can go on the other side. And for those cases, we just have to take, again, the value, evaluate the functions, we evaluate them and take plus 1. I'll give an example which makes a bit more sense. Sorry, I have pictures for this time. Okay, so we have this function here. This is after the if then else. Okay, the if then else that we consider is this one here. So the expression is x is strictly greater than 3. If so, we do s. Otherwise, we just go to f. So this is f. Okay, it's only defined where x is smaller or equal than 0 and has value 1. This one, for simplicity, is the function that we get when we evaluate the body starting from f. Okay, so this is the other one, from inside the body of the loop. So this one is only defined where x is greater or equal than 0 and has value 3. Now the condition is x is strictly greater than 0. So it's strictly greater than 0 means we exit the loop when we are strictly smaller, but strictly greater than 3, sorry. So this is the part of this yellow part here is where the expression is false. This yellow part here is where the expression is true. Now, when we try to find the function for the beginning of the if then else, we basically have to take this part where the function is defined, this part where the function is defined, increase by 1. And this gives us this function here. And you see this part is gone because this is the part that doesn't satisfy the condition. And this part here is in here, but the function is not defined in there, so it remains undefined in between the two functions. Okay, this is an extra other example, but basically it's where there is an overlap. So the two functions are the same, but if the condition is this one, so the condition will consider basically both of the, so there is no intersection. Sorry, there is no, there is an overlap between the two possible functions. We can only keep the x equal to this is the only overlap between the two functions. Like that. Okay. For the while is basically the same as the if, except that we have to do this in a fixed point here. Nothing strange. Yeah, I don't want to spend too much time on this. Okay, and then for the sequences, again, it's a backward analysis. We start at the end of the program. Oh, yeah, sorry.
I'm a little confused at what F is. I think
Yes, okay. The idea is basically it's the notational formation, so you're given some function after a statement, and you want to find a function, the ranking function that holds before the statement. So when I'm giving f here, this is the f, the function that is holding at the end of my statement. And I want to find the f that holds before the statement.
And these f's, they're like the instructions, or like you have the loop that while something.
Oh no, this is the ranking function that I have after the, so what I'm doing is, okay. So again, So this is your program. You have statement 1, statement 2, statement 3, and so on. And here you have a ranking function. Okay. So you have some function here, and what this operations are telling you is what function you have here. And what function you have here, and what function you have here.
And if the functions are like skip or check addition or...
These are skip, if, while, and whatever. These are the ranking functions. These are mapping from environments to ordinals.
Okay.
Yeah. So this f here is a ranking function, and what I'm trying to find is another ranking function. And yeah, sorry. It will make a bit more sense in a second, but yeah, essentially when you have sequences like that, well, you basically first do this one, you get a function which you feed to this one, and so on. Okay, so then when you have a whole program, where does the program start? Well, it starts with the function that has value 0 everywhere, because the program has terminated at the end. And now you want to find out from which environments the program can still terminate from here, from which one can still terminate from here, and from which one can still terminate from there. And so at the beginning you have all the environments in which the program always terminates. Yeah, which is this one basically. So you have an initial state, and the state is inside the domain of this function. The same here, and the rest one same before basically. Okay, now we don't have the time to see the abstraction, but I just want to give you an impression for how the abstraction is going to work before you forget everything that you're seeing. So the idea is we have a concrete ranking function here that we're building like this, or defining actually, not building. And now in practice what we want is actually define or derive automatically a ranking function for a program. So this one we will be able to compute, and what we're going to do is basically build it using piecewise defined ranking functions. And what they have, the important properties that we're going to have is whatever ranking function we will build here will be defined on a fewer set of states, on a smaller domain than the concrete function. So essentially what the abstraction will be able to prove termination for is a subset of the states that the concrete semantics can prove termination. So sometimes we're going to lose precision and we're not going to be able to prove termination for some states. But whenever we say that the program terminates, the program will terminate. So we will under-approximate the domain of the concrete ranking function, and we will over-approximate the value of the concrete ranking function. So essentially we will overestimate the number of steps that it will take to terminate in the worst case. Compared to the concrete semantics. And roughly the way the analysis will work